Hello everyone. So today we're going to talk about a very important tool in problem solving which is called as iteration. So when we iterate a particular thing, and this especially applies to recurrence relations, it actually significantly reduces the problem that we have to solve. And that's what we are going to see via today's example. So yeah, let's get started. So this is the problem number 1 from round 2 of the British Math Olympiad in the year 2015. And in this video, we're going to talk about recurrence relations, iterations, then you have certain book sessions for National Math Olympiads, and at the end, a similar but challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so what are they telling us? So the first term of a sequence is 2014. So x1 is 2014. Okay, great. 2015 year of the problem, x1 is 2014. Okay, perfect. Each subsequent term of the sequence is defined in terms of the previous term. Okay, the iterative formula is xn plus 1 is some sort of mumble jumble, right? And they want us to find the 2015 term of the sequence. Okay, great. So we really only have a couple of pieces of information, the first term and the iterative formula, right? The recurrence relation. Xn plus 1 is root 2 plus 1 times xn minus 1 divided by root 2 plus 1 plus xn. Okay, that's great. So what you can maybe do is try and find the second term, third term, fourth term. But you see that these numbers will be quite large and they'll be irrational. So you're really not making any significant progress by just finding random terms. So what you can do is you can try to find out the value of xn plus 2 in terms of xn. So what I would do is I would first find xn plus 2 in terms of xn plus 1. But I know the value of xn plus 1 in terms of xn from this given relation. So I would be able to find the value of xn plus 2 in terms of xn. Okay? Great. So xn plus 2 would be nothing but root 2 plus 1 times xn plus 1 minus 1 divided by root 2 plus 1 plus xn plus 1. How did I get that? Well, I just put n with n plus 1 in this relation, the given relation, and I got xn plus 2, pretty standard stuff. And now what? I know for a fact that xn plus 1 is root 2 plus 1 times xn minus 1 divided by root 2 plus 1 plus xn. And if I plug that in into this equation over here, I'll get something a little bit weird, a little bit complicated, but something that we can actually deal with. So this in fact becomes root 2 plus 1 times root 2 plus 1 times xn minus 1 divided by root 2 plus 1 plus xn, entire thing minus 1 divided by root 2 plus 1 plus root 2 plus 1 xn minus 1 divided by root 2 plus 1 plus xn. Now this may seem something very weird and something very complicated, but believe me, it's just looking like complicated because we haven't simplified it. And once you take the LCM and all, do a little bit of simplification, we'd actually get xn plus 2 as root 2 plus 1 whole squared xn minus xn minus 2 times root 2 plus 1, and in the denominator you would have root 2 plus 1 whole squared plus 2 times root 2 plus 1 xn minus 1. And that's great because I can apply like a little bit of factorization over here. I can take xn common and then I'll be left with root 2 plus 1 whole squared minus 1 negative 2 root 2 plus 1, right? And the denominator I would have root 2 plus 1 whole squared minus 1 plus 2 times root 2 plus 1. And again, just me simplifying the radicals a little bit over here, I'd get 2 plus 2 root 2 times xn minus 2 plus 2 root 2. And denominator again, I'd get pretty much the same thing. I'd get 2 plus 2 root 2 times xn plus 2 plus 2 root 2. And there should be an xn over here, I beg your pardon. Okay, great. So now we can just cancel this 2 plus 2 root 2s on all sides, this, and this. That leaves us with xn plus 2 is equal to xn minus 1 divided by xn plus 1. And that is why this is so great, right? Because we started with a complicated irrational looking expression, xn plus 1 in terms of xn, right? Then we formulated xn plus 2 in form of xn plus 1, which was again super complicated looking, not clean at all. But now we've gotten a form, and let me just maybe label that as equation number 1, which is very clean, and it can help us in a lot of ways. Now, how do we proceed further? If you actually notice something, they've given like kind of a hint in the question, the iterative formula. So they kind of want you to iterate. And what does iteration mean? Iteration means is doing the same thing again and again and again and again. Okay, so again, now what I'm going to do is I'm going to try and find xn plus 4 in terms of xn. And how will I do that? Well, in equation number 1, just substitute n with n plus 2 in equation 1. So I'll get x sub n plus 4 is equal to xn plus 2 minus 1 divided by xn plus 2 plus 1. Okay, great. But I know xn plus 2 in the form of xn from equation 1. So I can write xn plus 4 as xn minus 1 divided by xn plus 1 minus 1 divided by xn minus 1 divided by xn plus 1 plus 1. And once I kind of clean this out, I'll get xn plus 4 as negative 2 divided by 2xn, which is great because xn plus 4 simply becomes negative 1 by xn, which is my equation number 2. So you see, we've simplified this down even further. It has become even easier for us now to deal with the problem. This looks quite clean, right? It's not a major worry at all. But guess what? We can actually make it even easier. I'm going to plug in n with n plus 4 over here. Again, the same cycle. Xn plus 8 becomes negative 1 by xn plus 4. But then I can state that xn plus 8 is negative 1 divided by negative 1 by xn from equation number 2. So these negatives cancel and xn plus 8 becomes xn, which is an awesome result. Cause I start with any number k, I'll just go 8 places further, I end up with the same number, right? So x1 is equal to x9 is equal to x17 is equal to x25 all the way up till x2009. And why did I stop at 2009? Well, I could have gone x2017, x2025, but I want to find out the value of x2015. This is what I have to find, and these terms are ahead of that, so I don't really care. And all of these terms are equal, and they're equal to 2014 because in the question they've given us x1 is 2014. So x2009 also becomes 2014. Great. So now what I'm going to do is, if we maybe just observe equation 2, right? Equation 2. What was equation number 2? Let me just maybe rewrite that. Xn plus 4 is negative 1 by xn. Just plug in n is equal to 2009 over here. I'll get x 2013 is equal to negative 1 by x 2009. So that implies x 2013 is negative 1 by 2014. And if I just look at equation number 1, equation number 1 was xn plus 2 is xn minus 1 divided by xn plus 1. Equation number 1 actually. Now, if I plug in n is equal to 2013 over here, I'll get my 2015 term, which I want to find, which is x 2013 minus 1 divided by x 2013 plus 1. And I do know the value of x 2013, which is negative 1 by 2014 minus 1 divided by, this should be actually plus 1 over here. Yeah. Divided by negative 1 over 2014 plus 1. And once you really simplify that, you'll get x 2015 as negative 2015 over 2013, which is the desired answer. So yeah, really hope you learned something from that. And what we were essentially doing over here is we're just iterating. We're just repeating the same process again and again and again. So we started out with xn plus 1 in terms of xn. Then we moved on to find xn plus 2 in terms of xn. Then we moved on to find xn plus 4 in terms of xn. Then we moved on to find xn plus 8 in terms of xn, right? And what we actually realized is that xn plus 8 just so happens to be the same as xn, which was the critical result that we needed to solve this problem. And after that, it was just a matter of competition and we figured out the answer. So yeah, really hope you learned something from that. Okay, so here's some book sessions for National Math Olympiads: Elementary Number Theory by David Burton, Problem Solving Strategies by Arthur and Gell, Functional Equations by Venkatachala, Problems in Plane Geometry by Shadigan, Elementary Number Theory by Sierpinski, Graph Theory by Harari, and Combinatorics by Brualdi. Okay, so at the end we have a similar but challenging problem, and I want you to find the 22nd term of the sequence, which is defined by this recursion, given that the first term is 1. So x1 is 1, and I want you to find x20, 22. So maybe give it a try, and if you're able to make any progress on it, let me know in the comment section. Until then, I'll see you in the next video. Thank you very much, and bye-bye.
The programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.